Welcome back, everyone. I'm happy. Hello again. Happy to be here again today. Hope you still have in mind what I have talked about yesterday. I mean, if not, there's not a problem. You can ask me again what I'm going to speak about.
Remember, erasure is a cost.
Yes. So let's see. I will try not to be so long. But let's see. I mean, please stop me in any case again if nothing is clear. So we got a very nice talk about quantum network from Bill this morning. So I'm going to speak about quantum network at different kinds, as you know, a little bit already. And I will not go so far, technologically speaking, as Bill was trying to do this morning. But to give you some bunch of idea that I think are interesting to look at in continuous variable regime, especially because there is not so much there on this regime in this case. Okay, so let's start, and let's start about considering continuous variable cluster state as a kind of quantum network. If I want to replace is imagine that you want to do a quantum internet with it, okay? Well, I'm going to speak more a kind of local area network, just to consider that in any case, what I'm going to speak about is not going to be a very long distance. So just to recall you, what I have told yesterday is that we have the resource to build in the lab this kind of network where we have different frequency modes of optical field and different time bin modes. So Bill also was speaking about multiplexing this morning, and this is really a kind of idea that you can have in mind. I also show you very last yesterday some results about the fact that we can have a bunch of modes with squeezing that can build this network at telecom wavelengths. And also that we were trying, so this is actually, I didn't show yesterday, but that also in this scenario, we were able to build some very small network at this wavelength. So the idea is that now I would like to distribute the node of this network, okay? And so really because I'm at the kind of wavelength that can be distributed by using the multiplexer. And again, of course, I'm going to look at a small distance quantum network. Why? Okay, I will start by speaking about what I call the elephant in the room. I don't know, well, it depends. Probably if you have never seen continuous variable quantum state before, you don't know it, but it's very well known that continuous variable state of the kind I've shown you, so the squeeze state and the I mean, Gaussian entangled state are very fragile against losses. So here I'm showing you, I mean, it's a very stupid plot that I did yesterday, meaning that you remember I was showing you that a very typical way of measuring squeezing is that you plug your the output of the homodyne detector on a spectrum analyzer, and while you're scanning the phase of your local oscillator during time, you see that you go from the squeezing and time squeezing quadrature. And here I'm considering squeezing of 3 dB, which is of the same kind that I can produce in the lab. And so this is the black curve without any losses. Okay. If you start to add losses, what you see is that you decrease the squeezing, also the anti-squeezing a little bit, but also actually what you get is that it's no more symmetric at all. So you got much more anti-squeezing. Anti-squeezing is kind of noise. Anti-squeezing is the fact that you have a variance that is larger than the variance of the vacuum. So it's thermal noise actually at the end. And this is what you get. So the red curve is what you get if you consider that you have 1 dB losses. So probably the people that work a little bit with fiber connection, you know that this could be a kind of a very typical losses that you can have when you use a fiber connector. for sure you can do better. I mean, I'm just taking a typical kind of situation. And actually you see that the squeezing is reducing from 3B to 0. Is less than 0.5 in squeezing, and then you have more than 0.5 in anti-squeezing. So, and this is just by looking at squeezing itself. I'm not looking at, for example, security requirements of the specific protocol that they're looking at, as I used to do. That probably actually, I mean, you're already dead here. I mean, if you consider what is going on. So the idea is that, for sure, actually, as also Bill was mentioning this morning, probably are going to have a network of network, and also you are going to have some local networks. So the idea is behind it is that maybe we can try to exploit some continuous variable graph states as a local area network, because it's different than the discrete variable case with other feature. And then maybe going farther away by using more discrete variable encoding and the kind of encoding that you're used to. So this is the idea that is behind some different work that we have done. So a first one is a very short distance, because it's a really quantum communication protocol that is done in the lab, but was done in the optical table of the lab. And just to give you again the idea that probably there are protocols that are used to look at in the discrete variable regime, but you can also do in the continuous variable. So this specific one is the secret sharing protocol. So you have a network of, in this case, 6 people, mainly 5 people plus what is called a dealer. And so this is really the kind of network you can build. So you have a node that are different modes, different frequency modes. And then the entangling connection that you see between them is the application of the Seaside gate. And in this kind of protocol, the secret can be recovered only if you have a collaboration of bunch of people there, okay? So in this specific one, you have the collaboration of 3 among 5 in order to recover one specific secret. And so what are the kinds of measurement that you do in this kind? So this is exactly in the regime I was speaking, meaning that you do homodyne measurements. So you have 3 of them that measure specific quadrature on their sides. And then you have the dealer that also adds a measurement on a public channel to the tree. So the tree should collaborate. What is the secret that decide to look at? So, I mean, it's a very simple protocol actually, is that in one of the nodes that is not collaborating, you have a specific mean value of quadrature, meaning you have embedded a coherent state, and then you can recover. And so I'm not going to speak about, it's just a linear combination of quadrature you can optimize depending on the protocol. So this is just to show that the kind of, let's say, network protocol that you can have in mind in discrete variable, you also have an equivalent in continuous variable. And what is showing these plots is the results where you have different groups of people that collaborate to recover the secret, and how it depends on the quantum resource that you have there. So again, in this kind of multi-mode Gaussian state, the entanglement, the squeezing are the same resource. So remember that I look at the quality of the cluster that they produce by looking at the squeezing of this operator that I call nullifier. And here actually you see that if you have some squeezing, so the fidelity that you can recover is higher than if you have no quantum resource. So this is just considered as a classical resource. Well, you see that you have some fluctuation. I mean, it's not the best experiment ever, meaning that, I mean, you can see that you have the same kind of fluctuation in the classical and the quantum regime that probably depends on the quality of measurement that you can exactly do in this 3 conditions. It's really the experimental limits that you can see at very specific case. Okay, so this is a very, let's say, simple and fully local experiment with network of this kind. And the other two things that I'm going to speak about are the case where we look at very large cluster graph state. But I'm going to do it in theory. We don't already have it in lab. I'm going to speak about routing. But when I speak about routing, I speak about entanglement routing, because this is really the thing that you can more easily do in this kind of network. So what I have in mind. So are two different scenarios. In one, actually, I have a network. So imagine that you have distributed this network to several nodes that have some distance. And what you want to do is that you would like to have two specific persons in this network that want to communicate, meaning they want to have the best entanglement connection ever to do some kind of quantum teleportation protocol. Okay, so this is really the scenario that I have. It's a very specific kind of routing. And I'm considering two different scenarios that corresponds to the easy operation that you can do in continuous variable quantum optics. What are the easy operations that you can do? Linear optics transformation, kind of interferometric scheme, or kind of local oscillator shaping in the kind of net I was showing yesterday, or measurement, homodyne measurement. And also I'm considering the scenario where the linear optics can be done globally on two parts of the network on the left side. On the other case, actually, I can measure any nodes at any time as I want. So I will start to speak about the right side, that is the reshaping of disentanglement correlation by using measurement. Even before going through the kind of protocol, in this work, we started to ask ourselves, what is the cost of producing a continuous variable network? Okay, a cluster state specifically. And if you ask me, so I mean, I was the experimentalist in the group with a bunch of theory people. I mean, for me, it's kind of very clear in the sense that for me, the cost is how many squeezers I need to have in order to produce this network. How many modes, how many different modes I have to squeeze in order to produce this network. And yesterday, I was speaking a little bit on the board about what is called the block Messiah decomposition. So if you have a pure Gaussian state, you can think that this can be described as by looking at the quadratic transformation given by the experiment that produced your network or your multimode quantum state. And the transformation is a symplectic transformation. That is, I mean, it's the transformation that comes when you have Hamiltonian that are the most quadratic in quadrature. And this symplectic transformation, can be decomposed in what is called the block Messiah decomposition. So you go from you have this kind of input-output relation, so the initial quadrature, and then actually apply the Hamiltonian, you get this S that can be composed in these three different matrices. R1 and R2 are orthogonal matrices, so they're describing basis change. And then you have this delta squeezing, which is the squeeze term of the different modes. Very often you can start from the very beginning. So imagine that you are considering, in any case, state where the mean field is 0. So I'm always speak about what is going on to the different variances of the quadrature. In this case, you can think that you start from a vacuum state and you apply this symplectic transformation. So it means that what you're applying are a product of this transformation on xi, but if xi is the vacuum, R2 has no sense because you are applying an optic interferometer to a bunch of vacuum fields. Well, at the out we have vacuum, nothing else. So these are the two parts of the transformation that are important. And in these delta squeezing, you are going to have a certain number of modes that are squeezed. That is different depending on the state that you want to get at the output. So actually, we did just this decomposition by considering different shape of graph state, of cluster state that you want to get. Okay. And actually, you can describe, I mean, remember I was giving you the theoretical definition of a graph state with the CZ, with an adjacency matrix, which is the one of the graph that you shape. So actually you take this matrix and you look at the eigenvalue of the adjacency matrix. And you can find that actually this is really what is giving you the number of squeeze modes that come out. Probably it's not surprising for you. I mean, it's kind of, well, you have a graphical structure, is the one that you use to build the graph. Then you have a specific decomposition for this kind of state, and you can see that actually there is a very close relation between the graphical structure and the number of modes that they squeeze and how much squeezing you need to have. And that's true. But actually, this solution was found before only for infinite squeezing, and we devised it for finite amount of squeezing. These are actually the one that you can build in the lab. Very good. And then you start to look at very simple shapes. Well, I mean, you increase or decrease the number of nodes, and then you consider the linear shape, the ring shape, the fully connected, what we call the diamond shape or the star shape. And actually what came out is that the last two are quite different compared to the other one. Because you have only two eigenmodes of the adjacency matrix. So this means that I have always to squeeze only two modes at the beginning. Of course, actually, it's not only about how many squeezers I need, it's also how much squeezing I need. And of course, this increase when you increase the number of nodes that you like to have at the end with the same shape. And we had to devise a measure for the cost. So this is a measure that the logarithm of this squeezing term. You can find another measure. It's not important, but it was just a way of putting together actually all this new information, how many squeezing you need and what is the amount of squeezing. And actually what came out is that if you look at this different network by increasing the number of nodes, well, these two are extremely cheap compared with the other one that mainly increase linearly with the number of nodes, which is something that, I tell you, you have a node, a quantum network that is done by different nodes. I increase the node and entanglement links. So you expect that you have an increasing in the cost, in the sense that how much quantum resource you have to put there. But it's not exactly the same with the different shapes. So these two, they always have two squeezers that experimentally is really the situation you like to have. I need to probably have to increase the squeezing if I want to have 100 nodes. Well, maybe I have just to crank up the pound of my parametric process, and I have only to use two if you are in the condition where you want to have different paths with different squeezing going to non-interferometers. Okay, and so this is already nice. And then we start to look at network coming from a complex networks model. So these are no more deterministic networks. So we were playing with models that are used by people that are experts in network science, that we are not actually. We're just recovering some specific model. Of course, the probabilistic model. So you have family of network that corresponds to specific parameter and then you run the model to have a specific individual of this family. So, for example, here you have what is called the Erdős-Regin network, is the one that is considered being totally random. Here you have the Barabasi-Albert, that was one of the first that we used to study the internet topology, where you have, probably you cannot really see here, but the idea is that you have some hubs that are more connection than other. You have the small world network. So this is built by having a totally regular network, and then you start to mess around some, to reshape around some connection. This is the network of the autonomous system that has been studied at a certain point, so it should be to be one of the famous representation of internet that you don't like, but I mean, it's not me that did it. and this is a network that is used to look at kind of protein-protein interaction in biological networks. So there were just models that were out there and they were using. And here actually we are giving the adjacency spectrum of the corresponding adjacency matrix. Of course, actually, these are numerical calculations. So as far as I know, again, I'm not an expert, but you don't really have theory, except for this one, where you can approximate actually the spectrum of eigenvalue for this adjacency matrix. For all the other models, you don't have theory. So actually, you choose a specific family and you throw a certain number, 10,000 of this network, and then actually you make the spectrum, and actually you average over the model that you have chosen. Well, what come out about the cost is that in this network the cost is mainly linear, except for the fully random one that is a little bit super linear, and this is the one where actually you can have some theory about. And that's all about the cost of this kind of network. Okay, now we really want to do some routing protocol. So in this routing, what we were doing is to do some specific measurements at the nodes. So you have two nodes that you want to connect with an entanglement connection with the maximum entanglement possible given by the resource that you have in the network. And all the other nodes you're going to measure. And we're considering two specific choices. One is to measure the quadrature Q or the quadrature P. So the effects in the network structure is different. The quadrature Q, you really remove the nodes. In the quadrature P, when you measure the quadrature P, you remove the node, but actually you shorten in the sense that you link the two network nodes directly, okay? Very good. So we start to look at a bunch of network, and we came out again on the network that I think was shown up also at a certain point on the talk of Bill. That is, I mean, we call this diamond network, where actually you have the two people that you want to connect at the extreme, and then you have a lot of parallel paths going through another nodes here. And actually, if you measure P on this bunch of nodes that are between the two, well, you increase so here we use as a measure the logarithmic negativity for the entanglement at the ends after you have measured for the two nodes. You see that actually, if you have more nodes here, you are increasing, following this formula, the negativity that you get, the logarithmic negativity that you get at the end. So we came up with an idea of, if you want a naive routing protocol, meaning that if you take a very large network, what you're going to do is to look for all the structure where you have this parallel path linking the two nodes that you want to link at the end with the maximum entanglement possible. And what you're going to do is that in this parallel path, you measure P this way, in the same way you do in this diamond network. And then we wanted to compare with kind of other naive way of doing this measurement, that is either the shortest protocol, meaning that you just look for one path that is linking with a node in between the two, and then you measure P in this path, and then you measure X with all the other, meaning that you destroy all the other nodes, or the one where you measure P everywhere, okay, in all the other nodes. And okay, these are the results. So this graph is awful, okay? I know. But this was the way of putting all the things together, try to have a comparison. Actually, in green, yellow, and blue, you have the results for the three kind of routing. And in gray is where you gain something in logarithmic negativity at the end by using our naive protocol. So what you have in this axis, the node number, meaning that this protocol is done by choosing one of the two nodes being the hub, if you can define the hub in the system, and then you look at making this routing with all the other nodes around. And so what you can see that in general, in this case, I mean, in average, you gain by using this kind of naive approach where you look the structure that you know actually that can give you some advantage when you measure in P for routing these two specific nodes. And also the other point, so is that, of course, at the beginning, you have to look for this path. You have to decide how long, how many steps you want to do. And this calculation, if you do in this kind of random network complex model, does not take too much time. So because these are still out there kind of sparse network, so getting a look at the structure before starting the routing protocol is not time consuming compared to the also the fast protocol, that is the one that you don't think anything about and you just measure P totally random. Okay, so this is kind of fun. I think I also have the picture for a specific. So if you take one of the realization of the Internet of Autonomous System with 1,000 nodes, well, here you have in red for this specific 2 nodes. So this is the hub, and this is the other node. The parallel path that have been selected in order to do this parallel path. Increasing actually of the entanglement in this specific entanglement routing protocol. So it's a fully theoretical little game to play. So our interest was to really look at in the theories, the fully theory side, what is going on when you take very large continuous variable graph state. With the idea that actually these graph states can be reshaped more easily than other let's say, quantum internet realization. The second one that we were looking at is the one where we want to reshape via linear optics transformation. Oh, there's a lot of stuff written, but I'm going to give the main idea. So what is the idea? You have a network that you have produced, and then you have shared the different nodes to 2 different providers. And then you have a client that this provides that they want to link. So again, it's a fully theoretical little game that you want to play with this kind of network. Nothing serious. I'm not going to implement this network tomorrow in my infrastructure in the lab. And that is that you want to have these 2 providers, pi 1 and pi 2, just do specific linear optics transformation in order to connect with, again, an EPR link to specific nodes on the 2 sides. And we want to do it with just passive unitary. So this problem has already been tackled with general symplectic transformation. And in a way, it's not surprising that with general symplectic transformation, you can do what you want. Why? Because symplectic transformation includes squeezing, okay? So you have a squeezed entangled network, or meaning a multimode entangled network, meaning that the operation that you use to build this network is squeezing and linear optics. So if I give you the full power of doing squeezing and linear optics, maybe it's not so surprising that actually you can reshape the network as you want, because you can also do actually the linear optic transformation that bring you back on the squeeze basis, and then you can unsqueeze everything. You can resqueeze as you want and generate the network. So of course, as a global transformation, this also works every time. When you put the constraint that you want to do just 2 local transformation or 2 global transformation if you want, does not work always, but still you have a lot of power. Here we want just to work with only linear optics, so only linear optic transformation. So at the end of the day, what we would like to have, so again, this is a bunch of formula, is that the two nodes that you want to link in the network, they are going to have this covariance matrix. So the covariance matrix is defined as, the covariance is of different quadrature, okay? And this is the one that corresponds to the famous EPR state that I was showing you. Why I'm showing it? Because this is actually the easiest, let's say, quantity that you use to fitness actually the protocol that you use in order to look for these two linear optic operation in order to get the specific entanglement correlation. So what we do? Well, actually, we run an evolution algorithm that maximizes the fitness function. That is actually that given the two network, you look at the covariance, sorry, the two nodes that you want to connect, you look at the covariance matrix of these two nodes, and you want it to be as close as possible to this one, okay? You can have two different kind of results. The one that we call ideal routing, which is the one in really you are able to have results where the covariance matrix is very close to this one. The second one is imperfect routing. So the two nodes are entangled, but less entangled than so you vary this value actually around, but still they are fully disconnected for the rest of the network. Okay, this is what you want at the end, is that the two nodes are maximally entangled given the resources you have at the beginning. And this means that they should be fully disconnected with the rest of the network. We were again looking at a very specific structure, the regular one, and we're looking at grid structure and fully connected network, okay? And the grid structure is kind of surprising, maybe or not, because depending of if it's composed by double an even number or an odd number of nodes, you can or you cannot do this operation, okay? We don't have the full explanation. I have a colleague very recently was telling me, yeah, yes, I have, we have to discuss. So still waiting for this discussion with him. Probably it's linked to some symmetry of entanglement and the kind of operation you can have when you have odd or even number of nodes. But actually, well, we're rerunning the algorithm and we found this solution. I mean, this was the case for up to 100 nodes on this grid structure. So the idea is that you have, for example, all the blue nodes that belong to one of the providers. So Alice can do the operation. I think Alice is more on the red side. Bob can do the operation on the blue side. And you want to have either a routing between one node in Alice's side and one node in Bob's side. And actually, in this case, if you have uneven grids, meaning that the side of Alice or the side of Bob is even, you cannot do. While if you have an odd grid, you can, okay? And you cannot do anything, in any case, if you want to do the routing between two nodes on the same side. And the fully connected network is totally, is really different, is exactly the opposite. Which is in a way not surprising because the fully connected network is the one you have the most of entanglement. So probably, I mean, you cannot really destroy very easily the entanglement by just doing a local operation, and that does not destroy the rest of the network. And again, we're looking at complex network shape. Here again, you have three different models. And well, I can go through all these specific number where actually this is the purity that we get at the end. At a certain point, well, I think I discussed with someone yesterday about which kind of metrics you want to use for looking at the fact that you have a good protocol. You can use the fidelity. In our case, we're using the purity because really what you would like to have is to fully disconnect these two nodes with respect to the rest of the network. Of course, I mean, this can be done only if the purity is very high. And so at the end, we decide to use this metric. And here, for example, you have three different conditions. So Alice is an hub node, and Bob is a node with lower degree. Or you can have two nodes that has a maximum distance in the graph, or you can have two nodes with very low degree. And you see that in average, mostly everywhere, the purity is quite high. So meaning that again, this random complex network model seems to be not too bad if you want to do this kind of protocol in this scenario, so of course I'm speaking about graph that represent continuous variable entanglement network. One point, because probably it's not fully clear, but so this is the network structure, meaning that this is how the nodes are entangled each other. Blue and red, it means which one are on one provider side and the other on the other provider side. So actually the physical condition is this one, if you really want to have a picture. So you have a provider here with all these nodes, a provider here with all these nodes, and you have this kind of link between the different networks. At the end of the day, you are interested to have two specific nodes, one here, one there, that are entangled, meaning that you want to have this connection. You see that the rest of the picture is blurred because I mean, I don't care at all what is going on with the rest of the graph, meaning that at the end, the other nodes maybe are not a graph in the sense that I defined at the beginning, meaning that these are really the node, I mean, the graph that I described by having a squeeze state where I apply the Seaside operation. So I was telling you yesterday that the multimode Gaussian state is a larger family than the cluster state, the specific subclass. So I mean, I don't care about the fact that at the end, this is a cluster state. I just care that it's fully disconnected with the two nodes that I'm interested in, I really want to have. Yeah, this is exactly what is written here. And I mean, we don't really have yet the full explanation, but we started to look at some other specific transformation, meaning that I was speaking about the block messiahs, the general idea when you have pure state to decompose this multimode entangled state. But you cannot have always pure state. And for example, if I just consider two parts of this graph, of course, the subgraph is not going to be pure because you have entanglement correlation between the two. So the transformation that you use to decompose this network in order to see what are the resources that you have to put in it, in this case, is called the Williamson decomposition. And the Williamson decomposition, what they are decomposing actually is directly the covariance matrix here. And you can diagonalize it in a way where you have sigma, this is a diagonal matrix, and then you have you have the symplectic transformation on one side and the other. This diagonal has elements that can be equal or larger than the famous sigma 0 that I was giving yesterday. So meaning that corresponds to the vacuum value. So when these elements are larger than this, it means that I have a thermal state, okay? And the symplectic can be already been decomposed. So the most general transformation for non-pure state, multimode Gaussian, is the fact that you have thermal resource at the beginning, linear optic transformation, and then squeezing and linear optic transformation. So this is the most general way of looking at it. So actually we were looking locally at this, if you want, thermal squeezing spectral for the subgraph. And well, if you don't find exactly the eigenvalue of the one that of the covariance matrix for the two nodes that you want to be connected, well, actually you are not going to find the solution for this routing problem. So one condition is that the eigenvalue that you want to have at the end in the sub-node structure with only two nodes of the covariance matrix should be there from the beginning when you do the subspectrum of the two subset actually of the two. And in the case of internal routing, you also need to have value equal to 1. That means that you can do some kind of linear optic transformation that are more connected to fully pure state, meaning that you can disconnect nodes on the same local network. And this is actually, I mean, it's just the general idea that I was describing, giving you a little bit of intuition that in the kind of graph that I'm building on. So I was telling you yesterday that actually the squeezing and the entanglement in Gaussian multimode quantum states is exactly the same resource. And that's true in the sense that the entanglement comes from the fact that you have squeezing. at the beginning. So it's really the ideal picture when you have two squeeze states coming on a B-split. At the output, you have the entangled state. But you need the B-splitter. So what is generating the entanglement correlation, and also what you can use to disentangle is really the local operation that is given by this passive optic transformation, okay? And if you have to look somewhere, so this is the general decomposition that you can have for this covariance matrix. So it's exactly what I was telling you. Any multimode quantum state, non-pure, can be described as having a set of thermal states, okay? And then you do a basis change, meaning you start to mix. Maybe you can have thermal state at different temperatures, so you mix on different channels. Then you do squeezing, and then actually you do again a linear optic transformation, and actually you're mixing again this. And what you can think is that the one that is really creating the entanglement, and so probably the one that can destroy the entanglement when you look at this symplectic spectrum locally, is this R1 or this R2 here, because it's the one that is mixing the squeezing. So if you don't know actually where to look at, probably you have to look at this decomposition, this transformation, to see if you can do this routing in your specific graph. Okay, I'm finishing this first part. Do you have questions? I know this is kind of very, I mean, again, this is kind of a little game that they wanted to play, not to build this kind of network and doing the routing protocol tomorrow, but to understand what are the rules of the game in this continuous variable network. So for me, it was not fully clear from the very beginning that, I mean, I can imagine if I give you EPR, I mean, network done by EPR couple as you are used to with in discrete variable case, and I tell you, well, if I want to add, I mean, more node and more link, I mean, of course, I'm increasing linearly my resource, I imagine. You can tell me, but within, which is not the case for this kind of network.
I am not like used to continuous variable, but I try to reflect negativity once. Do we have to first follow the Hubbard criteria or some before extracting the negativity, or we just put it in the value as we just extract it?
So you're speaking about the first protocol where I look at the logarithmic negativity.
Generally, between CV sets that are entangled, we just extract eigenvalues and calculate this negativity.
Yeah.
Or we do some stability criteria first and then.
No, we just extract and we calculate the negativity from the eigenvalue.
And usually we have noise in the covariance matrix, which I don't know. I've seen we are not included in the previous case. In the previous case, with the.
So in the other case.
Central.
Okay.
So I think we have not included the noise that may arise.
No, we didn't include. So actually, I mean, the colleague that was speaking about before that we still have to discuss is the second author of this paper was Frédéric Grossens. And I know they are still working on this kind of network, and they're trying to make more let's say, close comparison to the kind of graph state that you can build considering discrete variable case. So probably they are including more results on this on this side.
The noise terms, then it cannot decompose and kind of same like the closed systems. You have to, it becomes electron integration.
Okay.
I'm also struggling with this same. So
okay. Well, maybe we can discuss later. It could be very much interesting. Okay. So, I mean, if anything, the take-home message is that you have some specific protocol for which we have the full correspondence between continuous variable and discrete variable. That was the first one, I mean, the secret sharing protocol. Still, actually, it's not working with the same resources. So you have to think which one you would like to use. Of course, one can be more or less resilient and so on. And then the second take-home message is that sometimes by just taking directly what you're used to do in discrete variable case and applying the continuous variable is not maybe the best thing to do. probably is better to start to study this network on their native scheme. What I mean with this is the fact that it's very natural for continuous variable to look at first at measurement and linear optic transformation in order to manipulate this network if you want. And probably you can learn a little bit more also about what is the cost of this network if you want to build them, and which kind of resource you have to use.
How do you make sure that this is the graph you have in the computer?
So actually, I mean, a graph, okay. What you have is that if you have, at the beginning, you want to build this graph by considering a bunch of, so that way of doing it. So the graph, I was giving the recipe, the theoretical one at the very last. And this give you a class state, and you can define, for example, the value of the squeezing in the nullifier at the end that you want to have. Okay, this is actually a measure of the entanglement that you have on the link. And then actually this is fully defined the graph. And then actually what you can do is just to reverse and doing the block Messier decomposition in the case of pure state for getting back what are the components. Another way of well, I mean, the picture is really, I mean, is an important question because you can build in different way actually, but the picture is really this one. So at the output, you want to have a graph state. And the recipe they have done, the theoretical one, considered you have infinite squeezing, and then you have applied a specific. If you want, yes. I mean, what you fix at the end is the amount of entanglement that you have, which is exactly what you have for the nullifier, and the number of modes, and which node are connected with which who, actually.
Adjacency matrix and the covariance matrix are kind of same.
Yeah. And then actually what I mean, you go back in order to understand what are the resources that you want to. Another way of building it is that if I have a bunch of squeeze states that are all squeezed the same way, there is a recipe that is really based on, you apply on the covariance. I mean, you have somewhere I didn't put here, but the adjacency matrix of the graph, and is a linear optic transformation, very well defined. This is another way. The third way is that you start with a bunch of squeeze state, but you want to have just linear optics in the sense, the other one was with Seaside operation that also implies some squeezing. So you have to decide what it is. So, and I mean, it's not a naive question because define a network in this scenario, it really depends what you define, okay? And the reason to stick with the class structure is because it's very well defined, the state that you start with, the general graph state. Because otherwise, I mean, you can consider that any multi-mode Gaussian quantum state is a network. I mean, it's a choice. Huh? I mean, I had a discussion with a bunch of colleagues, but it's kind of a choice that is fully, I mean, you are not really defined what are the nodes, what are the connections, etc. So in the case of the graph states that have been taught for doing quantum information protocol, so maybe it makes a sense if you have to distribute something to distribute the graph state, is very well defined. Still, you have some degree of freedom because either you define what is the amount of entanglement at the end with the same number of nodes, or you define that you have a bunch of squeeze state at the beginning and then you apply the operator, or so you still have some degree of freedom that you have to use. Thank you very much. Yes.
So when you were looking at these various different kind of hierarchy graphs and graphs like this, how stable are they despite parameter fluctuations in your network?
So yeah.
You generate them. If I change one of the beta ratios just a little bit, does the rough behavior stay, or is it?
So, for example, the way that computer scientists that are very much expert of network in the classical side, they solve it, is that they run so many generation of this network that are kind of 10,000 of 10 million of this generation. That, of course, in the case of the quantum case is a little bit less possible to do because still, I mean, it's Gaussian continuous variable. So, I mean, you can handle, but what we did is 100 generation for network of 100 nodes, and already took a lot to do the calculation. So the answer is that I don't know fully. We did some tests, meaning that we did it 2-3 times, and actually, given a set of parameters chosen for this specific model, they didn't change too much. Still, the kind of metric that we are looking at is, in average, is it better, for example, in the first protocol than the other naive protocol? So it's not really actually a very well-defined metric. So actually, probably it needs to be more refined. But this is also the problem when you go through this kind of complex network stuff, is that there is no analytic, just heuristics. So you define a model. You have to declare what is the model, you define the number of runs you do, and then you tell, well, this is what I get as results. Is stable enough? I don't know. Probably you have to run many more times.
It'd be interesting to see whether you start from a scale-free network, from a random network, change 1 or 2 parameters
in order to go
into a scale-free network, and then.
Yeah, you can try to do it. Probably could be the best way to, if you really want to scan the full complexity in a more defined way. Yeah.
Is there an instance where your network?
So I cannot really hear you. Maybe can give you the phone, the microphone, because it's better probably.
Hello?
Yeah.
So is there like a specific instance in which your routing protocol just breaks? Like, for example, a specific like fidelity that you were concerning or whatever?
So well, actually, the kind of instances where the kind of protocol I was showing does not work is the too much regular network. So even what we're trying, for example, this naive protocol of routing with measurements, when you take grids, I mean, does not work very easy. I mean, it's not really the one that you will use for regular network, a very specific structure. But normally also the kind of cluster that have been defined to be the one that you have to use for doing multi-party quantum information protocol in the immersion-based scenario. They're too much regular, actually. So it's better to have this kind of random network when you want to do this kind of protocol. And in the very specific one, actually, is also the fully connected network. That, I mean, we already knew, because also when, for example, in the one where we do the linear optic transformation, even when you do it with fully symplectic, is the one that does not work. I mean, does not work in general if you just take a bipartition, a random bipartition of the two. Not always you find a solution for connecting two specific nodes on one side or on the other by doing symplectic transformation, because probably is too much entangled in general, the fully connected network. So this is really the one of the special case.
Also, one more like out of the blue question: is it something like observable, like as a phase transition or something?
I think you cannot really define a phase transition of it. You have no, I mean, it's not easy of network, the good parameters that you're moving in order to, I mean, I have colleagues that use this graphical structure and look actually at the change of the complex network structure to describe phase transition. That's so meaning that there is some connection with phase transition with this kind of network, but it's not what is going on. Ah.
I thought you wanted to know what they
I've been saved. Is it dangerous or not? Now that you have killed it.
So I thought that you turn around and saw it coming down the black one.
No, you know, I'm so focused that now I'm not. No, I'm not this kind of person. I'm a kind of countryside person. But if it was not dangerous, you should not have done. But okay. Okay, thank you for the question. Yeah.
So it is, let's say, the network, the other person, the 1% does not wear, and it's let's say a part of the entanglement, let's say 3 parting. So then when you measure the negativity, you will get some value, positive value for the entanglement. So for you it will be entangled, but the third party would be in the network.
Okay, I see.
Which I know, I don't know.
Yeah, no, I mean, we were discussing a lot about also which kind of entropy or negativity, I mean, entanglement definition we have to use also because also continuous variable can use different kind of probably, I mean, as we're kind of average on large size network of specific shape. So, I mean, maybe this could happen, but it's not really, or maybe it's just giving a general bias, but we wanted to compare specifically to different kind of routing protocol that you are using. I'm not sure that is giving a, but of course, yeah, this is something to think about that could give him an input. Okay, if you don't have other question, I will do I will stop now before going to the rest. So I was promising to be shorter than yesterday. We still have another one, but so you have some free time. Okay, and we are back at. If it's possible, it probably is the best, no? So that after that you're free, fully free. What do you think? It's okay? Okay, very good.